Hi there, this is Penelope. This is a short video on motion. It's an introductory video to mechanics for the Level 4 Foundation course here at WellTech. The motion of an object, for example a car or a satellite or a tennis ball, can be described using various quantities such as distance or speed or acceleration. Motion always and also involves the direction in which the object moves. So when the direction is important, the quantities of distance and speed, for example, are replaced by the quantities of displacement and velocity. Now, often the symbol for both displacement and distance is d, but distance is a scalar quantity, and displacement, for example, is a vector quantity. And we'll go over these again in the second video. But to start off with here, we need to look at how the distance and the displacement are often quite different. Here we have an example of a model train going around a track, and let's look here. This should be actually a B. So we're starting at A, we're going to B, going to C, going to D, and this distance is 2 meters, this distance is 2 meters, this distance is 2 meters, this distance is 2 meters. But if we take the distance from A to C, that's, using Pythagoras, the square root of 8 meters. So at B, the train has travelled 2 meters. By the time it gets to C, it's travelled 4 meters. By the time it gets to D, it's travelled 6 meters. And by the time it gets back to A, it's travelled 8 meters. But have a look at the displacement. By the time we've got to B, we've only moved 2 meters north. By the time we've moved to C, now we're looking at the displacement, we've gone effectively from A to C, which is root 8 meters, and it's in a northeasterly direction. At D, we've only moved 2 meters east from our original starting point, and by the time we get back to A, we've effectively gone nowhere. So 0 meters. So the distance travelled and the displacement are quite different. Here's an example of a couple of cars, and yes, I know they will crash unless something happens, but never mind. Suppose we've got this car is travelling 30 meters per second, and this car is travelling 30 meters per second, but in a different direction. Yet in both of them, the speedometer will be showing 30 meters per second. So we need to think, though, that the velocity is the change in displacement, because we do need to look out for direction, divided by the change in time. So if we were to use symbols, we'd have the change in d divided by the change in little t. Acceleration is when an object changes velocity. So it might have sped up, it might have slowed down, or it might have changed direction. All of these will have an effect on its acceleration. We'd say then that the object has accelerated. So we could use a similar formula. Acceleration is equal to the change in velocity divided by the change in time. So it would be the change in velocity divided by the change in time. And the unit would be, say, meters per second squared, or meters per second to the -2, like that. If we're using acceleration as a scalar, then we're not looking at the direction, then we'd say it was a change in speed divided by a change in time. There are five equations that you're going to use for kinematics, and we're looking here, we've got a uniform acceleration, the thing is going in a straight line, it's a time interval t, and we've got all these equations here, a set of formulae which we call the kinematic equations of motion. And usually t is in seconds, displacement is in meters, and we talk about the initial velocity, which would be in meters per second squared, and the final velocity, which would also be in meters per second, not meters per second squared, but meters per second. And acceleration would be meters per second squared, like that. Now, in the second one here, that bit is actually the average velocity, and sometimes we can write that as v bar, so we could replace this by saying d equals v bar times t. If you want to know the derivation of these, if you want to know where they come from, most of them can come from this diagram here. So we've got time, we've got velocity, and we've got some object that starts here at v initial, and this has got a slope a, and we end up at the final velocity. Let's make that a bit longer, and this is our time t. And if we were to work out the area, this bit here is the final minus the initial, and the slope is a, and the area under the curve, or under the line, is the displacement. So you can work out those 5 formulas just from this diagram. We won't, but you can. As an example, we have a car, starts from rest and accelerates with a uniform acceleration of 0.5 meters per second squared in a straight line. And the question says, what speed does it reach after accelerating for 4 seconds? Fill in what we know. It starts at rest. So the initial velocity is 0. The acceleration is 0.5 meters per second squared. And the time is 4 seconds. We need to find the final velocity. So using the appropriate formula, we're going to say that the final velocity is the initial velocity plus acceleration times the time period. We know all of these bits. We know that, we know that, and we know that. So we can just substitute in. The initial velocity was 0. The acceleration is 0.5 times the time. And we then get our final velocity as being 2 meters per second, or meters per second. A second example is where we have a ball initially travelling at 4 meters per second, and it slows uniformly. It's travelling up a slope, and it stops 16 meters up the slope. So we've got a ball, it's going up a slope. The slope is 16 meters long, and starts with an initial velocity of we're told it starts with 4, and then at the end obviously the ball has the final velocity of 0 because it's stopped. Right, so it's 16 meters up the slope and it starts off 4 meters per second. Let's see what we've got. We've got the initial velocity as 4 meters per second. We've got the final velocity as 0 because it's stopped. We've got the distance equals 16 meters. Now we're going to use this version that the final velocity is equal to the initial velocity squared plus 2AD. We know the final velocity is 0. The initial velocity is 4 plus 2 times the acceleration, which, we don't know that, times the distance, which is 16. Now, using some algebra, we can shift the 4 squared onto the left, and that leaves us with 2 times 16, which is 32a. Now, negative 16 equals 32a. Divide both sides by 32, negative 16 over 32. And that will be in meters per second squared, and that will equal 0.5, but it's negative 0.5 meters per second squared. So it's slowing down, which is what we'd expect. We'd expect the ball to slow down as it went up the slope. Part B says, how long does the ball take to stop? Well, let's use this version. We know that D equals VF plus VI over 2 times T. Let's fill in what we've got. We've got the displacement is 16. We've got that it's equal to 0 plus 4 over 2. The only thing we don't know is time. So 16 equals 4 over 2, so that's 2t. T equals 16 over 2. So the time, 16 over 2 is 8, and it's measured in seconds. Now, we could have used several of the others of those because we do actually know A, but this one seemed easy. So it takes 8 seconds to stop as it's going up the slope.